So, our today's topic is underfitting. Coming on to the table of contents, we have the introduction. What is underfitting? That is the difference between underfitting and overfitting, and good example for underfitting, how to avoid it, and then we go on to the conclusion. So, coming on to the first part, that is introduction. Now, giving you a good example, that is, if we consider a good machine learning model, it is said to be good when we take some custom inputs and it will give us a desired output that will help us in classification and also make prediction in the future data that the model has never seen. Now, if we want to check how well the machine learning model trains and generalizes to the new data, we have for that we have overfitting and underfitting, which are responsible for the poor performance of the machine learning algorithms. Now, coming on to the what is underfitting. Underfitting occurs in data science when a model is unable to capture the underlying trend of the data. It results in generating a high error rate on both training data and unseen data. It occurs when a model is very simple, that is, the input features are not expressive enough, which results in model needing more time for training, less regularization, and more input features. Now, when a model is underfitted, it will have training errors, poor performance. Also, it will not give us the desired output, and it will not cope up with the new data, which will hamper our classification or prediction task. A model is a good ML model if it generalizes any new data from the problem every day to make predictions and classify data. Low variance and high bias are very good indicators of underfitting. Coming on to the differences between underfitting versus overfitting. Underfitting versus overfitting. To be very simple, overfitting is the opposite of underfitting. It occurs when a model is overtrained or it contains too much complexity, because of it results in high error rates on test data. Overfitting a model is more common than underfitting one. The model is overfitting your training data when you see that the model performs well on the training data but doesn't perform well on the evaluation data. This is because the model is unable to generalize to unseen examples and memorizing the data it has seen. It will mug up the data with the training data, and when a new data comes, it doesn't cope up with the new data. As mentioned above, the model is underfitting when it performs poorly on the training data. This is because the model is unable to capture the relationship between the input example and the target value accurately. Underfitted models are usually easier to identify compared to overfitted ones, as their behavior can be seen using the training data. Below is a very good example, that is, as you can see, there are three graphs, that is balanced one, underfitting and overfitting. Now you will be watching and also guessing you cannot understand. So after this live example you can understand it. Now this is a very good example. As you can see, it demonstrates the problems of underfitting and overfitting and how you can use linear regression with polynomial features to approximate nonlinear functions. So this is our training data, and then we'll test the data and see the graphs. The plot which when we'll run this code will get a plot. So the plot shows that we want to approximate, which is a part of the cosine function. In addition, the samples from the real function and the approximation from different models are displayed. The models have polynomial features of different degrees. We can see that a linear function with degree 1 is not sufficient to fit the training model. We can say it as underfitting. A polynomial of degree 4 approximately gets into the true function. We can say the model is the best fit model or the best model. However, for higher degrees, the model will overfit the training data. It learns the noise of the training data, and that will know that it is an overfitting model. We evaluate quantitatively overfitting or underfitting by using cross validation. We calculate the mean squared error, that is MSE, on the validation set. The higher, the less likely the model generalizes correctly from the training data. So You can see this example and we will see the live implementation of it and also the graph we get from the code. So this is a Jupyter notebook code or the Python code for it. That is, these are the libraries we need, that is numpy as np, matplotlib, scikit-learn, that is pre-processing of the polynomial features. Now for the model 1 we need linear regression, cross validation score we need for the model selection 1, and the pipeline to include all the features. Now we need to fit the function. For that we use this cosine function, as you can see here. Now coming on to the initializations, we have used the random function to initialize. We have taken 30 samples, as you can see in the code, and 3 degrees as degree 1, degree 4 and degree 15. Now we have separated the one into x and y for the training and testing feature. Now we will plot the polynomial for degree, that is for degree 1, degree 4 and degree 15. Here, as you can see, we can use the plt.figSize to set this figure size, and also as you can see we can train our linear regression, as we can edit the linear regression feature into our model. Now coming on to the evaluation of the model using cross validation. As you can see, we have used scores equal to score cross val score pipeline using this, and the mean squared error, that is MSE. Now finally we have plotted using these functions, that is we have plotted the 3 data, and finally we have shown plt.show. So we will get a graph like this now after we run the data. After we run, you can see this. As you can see, these are the sample points, the blue dots, and this is the model line. You can see clearly how it underfits the data and doesn't even touch our samples. Here you can see the blue line completely identical to the true function and completely passes through the samples, which is a very best fit model. And this one is the true function, and this is the model which touches the data points but creates very low variance and very low bias, which creates a noisy and it overfits the data. So this was a live implementation of our code. Now coming on to the final one, that is how to avoid it, how to avoid underfitting so that our model will work perfectly. The number one technique should be to decrease the regularization. Regularization is usually used to reduce the variance with a model by applying a penalty to the output parameters with the larger coefficients. There are a number of different methods in machine learning which helps to reduce the noise and outliers in the model. By decreasing the amount of regularization, increasing complexity and variation is introduced into the model for successful training of the model. Now we have to increase the time or increase the duration of the training. Training the model for less time can also result in underfit model, that is to try the model for more epochs, ensuring that the loss is decreased gradually over the course of the training. However, it is important to make sure it should not lead overfitting and subsequently overfitting. Finding the balance between the two will be the best key, and a very important one to avoid underfitting is feature selection. We will select such features which will be important for the model building and the outcome, and will neglect other features. As you can see, there are not enough predictive features present, then more features with great importance or more features should be introduced. This process can increase the complexity of the model, resulting in getting better results and decreasing the underfitting. Now going on to the conclusion, so we can apply these things to get a good model. When we train our model for a particular time, the error in the testing data goes down. But if we train the model for long duration of time, then overfitting occurs, which reduce the performance of the model. So and also when we'll regularly create, then underfitting occurs. So we'll try to avoid by using this, how to avoid reduce underfitting methods, we can avoid underfitting, so that we'll get a good machine learning model with a good fit, so that, and which should be between a underfitted and overfitted model, so that we can make accurate predictions and perfect predictions. So that's all. Thank you.